Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem of quantum mechanics. Problem has been chosen from the book Quantum Mechanics Concepts and Applications by Nordine Zetley. Okay, author is Nordine Zetley. Book title Quantum Mechanics Concepts and Applications. Okay, as usual we first come to its statement. Consider a mass spring system where a 4 kilogram mass is attached to a massless spring of constant K equal to 196 Newton per meter. The system is said to oscillate on a frictionless horizontal table. The mass is pulled 25 centimeter away from the equilibrium position and then released. Part A. Use classical mechanics to find the total energy and frequency of oscillations of the system. Part B. Treating the oscillator with quantum theory, find the energy spacing between two consecutive energy levels and the total number of quanta involved. Are the quantum effects important in this system? Dear students, situation is quite simple. Not more conversion factors will be used, only we will have to convert this 25 centimeter into meter by dividing it by 100, then it will become 0.25 meter. Okay, for this purpose we will have to develop some foundation regarding understanding of this problem. Okay, so these 6 snapshots are being taken into consideration. Out of these 5 snapshots, first 2 have been selected from the book of Young Friedman, while other second snapshot, screenshot, which has been split in 4 parts, has been chosen from the book of Raymond Survey John Jude. Okay, anyhow, angular frequency for simple harmonic motion omega equal to k over m, where k is force constant of restoring force and m is the mass of object. Okay, then frequency of simple harmonic motion f equal to omega over 2 pi equal to 1 over 2 pi into k over m, where k is force constant of restoring force and m is the mass of object. Okay, omega is angular frequency. Okay, yes students, it is here our discussion whether we denote frequency by f or nu. Okay, usually in quantum mechanics we denote frequency by nu. Okay, and one more thing about nu is that smaller case of nu and smaller case of epsilon are to some extent similar, that is similar Greek letters, Greek alphabets. Okay, however uppercase of nu as well as uppercase of epsilon are quite different. Okay, now the kinetic energy and potential energy for an object of mass m oscillating at the end of a spring of force constant k vary with time and are given as k equal to half mv square equal to this and potential energy u equal to half kx square equal to this. Okay, then the total energy of a simple harmonic oscillator is a constant of the motion and is given by E equal to half ka square. Okay, so these are the 2 basic expressions which we will follow. Okay, first expression is this: frequency equal to 1 over 2 pi k over m, and second is E equal to half k a square. Okay, so we have developed a sufficient foundation towards understanding of this problem. Okay, now part A, according to classical mechanics, frequency nu or frequency f is equal to 1 over 2 pi k over m. Okay, pi value is this 22 by 7, 3.14. Pi is a very special number, non-terminating, non-repeating. Its decimal representation goes endlessly. Okay, k is 196 Newton per meter. We have written meter in the denominator. Okay, mass is 4 kg. Okay, then in place of Newton we have written here, dear students, 4, when 196 divided by 4 will become 49. Okay, 49 divided by 4, 49 kilo in place of Newton is equal to kilogram meter per second square. So we have written it in this form. Okay, so from here meter will be cancelled with meter, kilogram will be cancelled with kilogram, and second square will in the denominator will remain, and it will become outside the denominator as a single s raised to the power minus 1, and we know that second inverse is equal to hertz. Okay, so new frequency will become equal to 1.115 hertz. Okay, now we use other expression also, E equal to half k a square equal to this, and hence energy E becomes equal to 6.125 joule. Okay, part B, according to Planck's postulate, the energy of an oscillator of natural frequency nu must be an integral multiple of h nu, that is E equal to nh nu, where n is equal to 0, 1, 2, 3 and so on, where h is a universal constant, that is h is the Planck's constant, and h nu is the energy of a quantum of radiation. Actually here we have not shown a table. Table is same which we have shown many times in previous. Okay, in that table value of h is given, etc. Okay, however that table is not very much necessary in every case, because we have shown that table many times. Okay, where h is a universal constant called from Planck's constant, h mu is the energy of quantum radiation, using the values of E, h and u in equation number 1. Okay, the value of E we have found in the previous step. Okay, E and n is the same, n we have to calculate, and h is the Planck's constant. Okay, which is taken from table of physical constants, and nu is given in the statement, which is equal h into 1.1. Yes, nu we have found here. We have found not given in the statement. We have first found frequency nu. Okay, this frequency nu is also being used in the expression under consideration. Moreover, value of E 6.125 joule is also being used. Okay, so this value has been calculated in the previous step, and this value has been calculated in starting of this problem. Okay, and this is the value of Planck's constant. Okay, then just simplification, nothing else. After simplification, our n becomes equal to 0.83 into 10 raised to the power 34, or if we convert it in 8.3, then this 34 will reduce to 33. Okay, 8.3 into 10 raised to the power 33. Now we come towards the part B, where it is asked, are the quantum effects important in the system? No. Its answer is no, and proper wording is no. Yes, this is the proper wording. No, the quantum effects are not important in this system, because the energy of one quantum, that is h nu is equal to Planck's constant. This into nu, this is equal to 7.39 into 10 raised to the power minus 34 joule in comparison with the total energy 6.125 joule is so small that it may be neglected, and the number of photons is very large. Okay, due to this reason our answer is that no, the quantum effects are not important in this system. Okay, this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.